Hello everybody and welcome back. So in this final lesson for the week we're going to just be finishing off the practical examples that we started in the last lesson, and then after that we'll be moving on to some pretty cool advanced vec stuff. So let's dive right in. Alright, so let's get started. Now the first one we're going to do here is talking about vector length, and so this involves not only a little bit of vecs, but actually also understanding vector mathematics. So if we take our normals, so I've using this rubber toy test geometry that you can get just on SOP level, just to have something that has much more complex normals than just on a sphere. And I'm displaying the normals here so you can see them, right? And if we want to alter any vector, but in this case we're going to particularly be looking at normals, it's important to understand that vectors have two components to them, right? So they have magnitude and direction. Magnitude is the length of the vector, and then the direction is obviously, the direction of that vector. So for example, velocity. If something is moving forward, like let's say along the z-axis, right, at 3 units every frame, then the magnitude of that vector is going to be 3, and then the direction is going to be 0, 0, 1. So because it's not moving along the x-axis, not moving along y, but it's moving along the z-axis, right? Now that velocity would be represented as 0, 0, 3, kind of like this, okay, because it is actually equal to the magnitude, which is 3, multiplied by the direction, which should be normalized. Now what we mean by normalized is that the length of this vector is 1. Now it's easy to see that this is 1 in length because it has nothing in x and y, but if it was not exactly along the z-axis and it was maybe aligned, I don't know, some random vector, then it would be a lot harder to see if it's normalized. But essentially the length of the vector needs to be 1, because then when you multiply anything by 1, it becomes exactly that number. So in other words, multiplying a normalized vector by 3 will give you the same vector, the same direction, but it will be a length of 3 units. Okay, so that's a little bit of understanding of vector mathematics, and what we're going to do is use vecs to do exactly that. If we want to alter a vector, it's often necessary or a lot easier to divide the vector into magnitude and direction. So we have a normalized vector, which is the direction vector, and then we have just a float, which is the magnitude. Okay, so we're going to take the normals, so v at n, right? But there's two functions we're going to use on this. So if we use the length vector expression, and I'm going to click on this and hit F1 to open up a help file for length. So all length wants is either a float or a vector 2 or a vector 4 to give the length of that vector. Okay, so that's really, really simple. It just takes one argument. So we say length v at n, okay, and we're going to want to store this in something. So let's just create a variable. So we're going to say float, and let's call this my vec len. Okay, you can call it whatever you want, right? And I'm going to hit insert. All right, so we've created a variable. Remember that this variable is only going to live in this script, so when I look under my geometry spreadsheet, you'll see there isn't any my vec len. It hasn't written an actual attribute, okay? But we have stored that value. And then the other part of this is that we're going to need a normalized vector, okay? So it is going to be a vector, and then we're going to call it my vec dir, okay, for direction, equals, and then the function we're going to use is normalize, and I will hit F1 on this to show you what this does. So again, it takes only one argument, which is a vector, and it is going to return the normalized vector of that. Okay, so we normalize the same vector v at n, and in this way we have split it into magnitude there and direction there. Okay, and if we had to multiply these two together, you'd end up with exactly the same result. So if we do that, we just say v at n equals, so we're overwriting our normals. We're overriding it with a new value, which is my vec direction times my vec len. Okay, and then we display normals. You'll see they're exactly the same. If I disable this, re-enable it, nothing is changing. Okay, so you may ask, well, why would we do that? The reason for this is because what we would, like, sometimes you want to set conditions, or you want to maybe add to the length without altering the direction, which can be quite difficult. You then need to figure out for each point the direction of that vector, and then add another vector that's along that same direction. It's just much easier to separate it into length and direction, add to the length, and then multiply them again. See, if we took something like v at n and we multiply it. Okay, so let's just disable this and just say v at n equals v at n times 2. Right? You'll see that the directions don't change. The vector just grows to exactly double the length. Okay, so you can just multiply vectors by floats, as we see, here. But actually, that's exactly what we're doing here, multiplying a vector by a float. So if we just wanted to increase the length by a certain percentage, then just multiplying is what we can do. But it becomes a lot more difficult when we want to just add a value, or maybe we want to clamp the length of the vector. Okay, so we can do something like that. So now, because we've separated, we just say my vec underscore len plus equals 2. Okay, so, and then we would obviously have to re-enable this. So now here, instead of just multiplying, we're adding a static value. We can add 5, or we can even add negative 1 or something like that, So we can do really strange things with it. We could even clamp this, so we could add 1 to it maybe, and then say my vec len equals clamp, and we could clamp it between, let's say, a value of 2 and 3 or something like that. Oh, sorry, I forgot the semicolon. And we need to say my vec len here. Okay, so we can do a whole bunch of weird things to alter the length of this vector and then multiply it back by the direction. Or alternatively, what we could do is alter the direction and then remultiply by the length. So you might want to actually bend some of these normals, and it's a lot easier to do that with a normalized vector, and then but maintain the same length. So then you just multiply. After altering the direction, we then multiply by the length. Okay, so this is something you'll probably need to do quite often, not necessarily only with normals, but a lot of vectors. You'll need to split them into length and direction. Also keep in mind that if you take the length of something like a color vector, so RGB, then the length is actually the same as the luminosity. So the luminance of that color channel. Okay. So it'll return a float, which will be a grayscale value, 0 to 1, but it will essentially be the brightness, how intense the colors are at that area. In other words, how close to white they are, or how close to black. It'll be 0 to 1. Okay. All right, so now we're going to move on to the next example. All right, everyone. So in this example, I'm going to show you a little trick about unique IDs. IDs are very, very powerful. You're going to use them often in Houdini for a wide variety of things. It just helps keep track of which point is which point without you relying on point number, because the fact is point numbers are an index. They keep changing to make sure that there are no gaps. Okay, if there are only, like in this case, we have 40 points, then they will be numbered from 0 to 39. As the points increase or decrease, they will always fill every gap in the index. Okay, whereas IDs is a unique stamp on each point that it remembers, you know, what its original point number was or what primitive it came from. It depends how you set the ID, but basically it's very vital to be able to set IDs correctly. Okay, so I'm going to show you an example, because sometimes just doing IDs in the normal way is not enough, right? And we're going to use Vex to fix a common problem. So I'm just going to walk you through my system quick, just so you can see what I've got. So I've drawn a little curve, smoothed it out just to make it look a bit better, and then I'm setting ID here based on point number, right? Now you're often going to want to set ID from point number whenever you're going to do something like you know, a copy, or if you're going to simulate and generate something from this, because before the geometry begins to duplicate itself, you want to know from its source which point was point 0 and which was the end. I mean, you know, in this particular case, you may want to create a gradient attribute that goes from 0 at the root all the way to 1 at the tip. If this was a strand of hair, you'd need that kind of attribute, or you just want to be able to know, okay, halfway along this curve, well, where is it? Then you can go to that 0.5 value, but only if you've been able to actually create a gradient attribute out of this. So just having IDs from 0 all the way to, you know, in this case, to 81 is going to be vital. Okay, so we're creating an ID there, and then over here I'm deleting the primitives. Okay, and now the reason for this is because this is where things get difficult. Basically what I'm trying to mimic here is an issue that we run into often, where when we're copying, we kind of want to keep track simultaneously of the 0 to 1, you know, unique IDs along these I guess group of points that we're copying. Okay, so we want to know 0 to 1 on each of these curves, and at the same time we want to know which primitive they're part of. So we want this to be 0, this to be 1, this to be 2, so that we can simultaneously do gradients and copy values across all of these. You know, maybe we want to even join all of the, like whatever point number this would be, so maybe 10 along the curve. We want to join them all to make a nice circle over here by joining all of point number 10s across these lines. So we want to know where it is along its own individual line, but at the same time you also want it to have its own unique ID. So if we want to maybe randomize particle scale across all of these, if we use ID now after this copy, then essentially, so I'll show you here, if I go to my geometry spreadsheet, you'll see in the IDs there's duplicates. There's obviously duplicates because of every copy has then duplicated this point, which has ID number 5 or whatever it is. Okay, so then on this one there will also be an ID number 5, and then this one will also have an ID number 5. Okay, which we do want, but at the same time we also want to know its unique ID, right? So how do we reconcile this? Okay, so this is the reason why I'm actually deleting the primitives in this case, because with primitives it's easy to reconcile it. After the copy you just look at the primitive number. Okay, so if we didn't do this and we had a copy like this, we could just use the point, like your unique point IDs, which are no longer unique because they've been copied, so it goes 0 to 81. But then you'd use a primitive number, and then you reference each one individually, or you can reference, you know, the gradient. But we don't always have that luxury. Sometimes we don't have particles, we'd have, you know, just points. Okay, and sometimes we also want to simultaneously, like in one random attribute. So let's say we have it running something like a color. You know, if you use the color node, you can say random, give it a random color based on attribute. But you can't now feed it two attributes. You can't feed it the ID and the primitive number. Okay, So this is actually what we're aiming to do, is find some way of creating an ID that references both its gradient ID and then its primitive ID at the same time, so we can get a totally unique ID while still maintaining its gradient and primitive number. Okay. So in this wrangle, you don't really need to worry too much about this, although if you want to, you can kind of look at what I've done here, maybe see if you can figure out what's happening here based on what we've spoken about before. We haven't worked with blocks yet, so I will we'll get around to understanding this, but if you have been following, you should be able to at least figure out a little bit of what's happening here. Essentially what I'm doing is carving randomly back and forth along the timeline, okay? But I'm carving just by deleting points, because when you do a standard carve operation, first of all, it requires an actual primitive, and like I said, we won't always have access to a primitive. Sometimes these are loose points that are not joined in a curve. Maybe these points were created in a DOP, part of a POPSIM, so they aren't actually part of one primitive, okay? In this case, they were because I drew them this way, but what we're trying to do is replicate a difficult situation and then fix it using vex. Okay, so that's all that's doing, and then here when in my copy I am copying 8 times, but I'm also referencing that copy number with a channel reference and dividing 360 by that number, so that we get, as we change this, you'll see like if we only have 3 copies, then each one will be exactly 120 degrees away from one another so that it fills a full circle, okay? So that's just a cool trick if you want to, do basically a rotational copy. Right. So here's how we're going to work through this. So I'm going to put down a wrangle, and what we're wanting to do here is combine 2 IDs. Now, one of the problems though is if we just added, let's say we took the IDs, and I mean we know at the center here, at this very base point, its ID is 0, then its ID is 1, then its ID is 2. So let's take this one, ID 2. Okay. And if we just took its primitive number as well, so if we could somehow get a primitive number, even though this doesn't have a primitive, but if we could have this entire group of particles having a unique number, and then just add that, okay, that wouldn't quite fix our problem, even though it may seem so at first. So let's assume that this group of points, so this curl, is primitive 0. And like I said, this is 0, 1, 2, 3. So let's take this. So this would be then 3 plus 0. So this would be ID 3. Okay. Now when we go over here to the next one, let's assume that this is primitive 1. So this would still have 0, 1, 2, 3, but it would be adding 1. So this would be ID 4, and this would be ID 3, which may seem fine because now they're unique. They're not the same as one another. But the problem is this is adding 1 to all of the numbers. So this, which is ID 2, 0, 1, 2, plus its primitive number, 1, is going to give us a value of 3. So this ID and this ID are now the same. So you see how it hasn't actually, by adding in the primitive number, it hasn't made them unique. It has just offset it by the primitive number. Okay. So first of all, let's talk about how to get an actual primitive number, even though we don't have primitives. And when you do a copy and transform, one of the options, which is off by default, is this copy number attribute. So when we select that on, it's going to create an attribute called copy num, which is going to be, we're creating 8 copies. It's going to literally create 0, 1, 2, 3, 4, 5. It's going to actually create an ID for that group of geometry. Like all the geometry, doesn't matter if it's points or primitives, whatever it was copied, will all get this value essentially stamped onto it, 0 to 7 in this case. Okay, because it's also an index. Okay, but because we don't actually have any primitives, and this here says that it is a primitive attribute, you'll see that it has created copy num, but it's actually got no geometry to write information to. So we're going to get around this And we can do this with a particle, like particles that have been simulated as well. So keep this trick in mind, is that you can use an add node and actually go under particles and just add a particle system. And what that's doing is adding essentially a primitive attached to a group of points. Okay, and that primitive doesn't have any, connecting lines, but it's essentially grouping all of those points into one primitive. Okay, so you see here it says one particle system. And that allows us to then write this copy num attribute, 0 to 7, okay, onto this particle system primitive attached to that group of points. Right. So now we have an ID that's unique per point, going from 0 to 81 at the end. Is it 81? Yes. Okay. And then also a number per particle system. And now we want to add these two together, but we want to add them in a way that gives us a unique number. And here's where the trick comes in. So I alluded to this in a previous lesson, but now we're going to do it, where sometimes you want IDs that are strings instead of integers. And the reason for this is when you add an integer, it adds the number. So 2 plus 2 is 4. But in strings, 2 plus 2 is 22. Okay? Because it just concatenates those two characters one after one another. And if we combine that technique with padding, so we have spoken about padding before in this course, but so padding it where we give a bunch of leading zeros. Essentially what we want to end up with is, let's say we're talking about particle number 2 on the particle system, and we're looking at particle system number 2. Instead of saying 2 plus 2, let's 2 plus 2, which is going to give us 4. Instead what we want to do is do 002 plus 002, and we want the result of that to be 002002. Okay. The reason why we want to pad it this way is also if we do the same where, so it's an actual, so we're adding strings like this, 2 as a string plus 2 as a string, and the result of that will be 22. Now that is closer to the solution we want, but the problem with this is that we have more than 22 points on our particles. Like on our original particle system, we have 82 points. Okay, which means that in this case, when we're adding 2 to 2, we're getting 22, but we're also going to get 22 when we're adding particle number 22 to particle system number 0. Okay, we're still going to get 22. Okay, so we want to just pad, just to make sure that we have enough essential like space, digits to work with, to not overwrite any values. Okay, so there's absolutely no overlap, and in fact there will be gaps. Okay, which is what we want. So this is what we're going to create now. Okay, but we're going to do this using a function called sprintf. Okay, so I'm going to explain this now. We're going to be storing and creating a string ID. So I'm going to say s at, and then I'm going to say my ID. Okay, and now I'm going to run this function. So it's s print, because we're printing a string, so it's a string print f function. Okay, so it's the printf function. I'm gonna show you now. Okay, so I'm gonna hit F1, and we're gonna have a look at what it says here. So the sprintf function formats a string. So it's the printf is a format print function, but it formats a string like printf, but returns the result as a string instead of printing it. So this is a bit complex to follow, but basically you can use the printf function in Vex to print values to your command terminal. Okay, so you can kind of check values and print things to the terminal, right? What this does is mimics that same printing, but returns it as a string which we can store in an attribute or a variable. Okay, and The reason we would want to do that is because the printf function comes with a lot of functionality that we need, okay? And they haven't up to this point created proper padding, because I showed you guys in a previous episode where we did padding in HScript expressions, which has that pad 0 function. But you'll see that in Vex, pad 0 is not a function. This is not a Vex function, okay? So it is so much easier to just rely on this printf function, which has a lot of functionality, okay? We're going to go through it just now. But we're using the functionality of the print function, but instead of printing to the terminal, we're just storing it as a string, okay? So I hope you guys are following. This can get a bit hairy, but try to follow along, and if you don't understand, go back and do this over again, or ask any questions you need to. Now, it's going to explain in here, if you read through it properly, that we're essentially using this percentage sign symbol to show where we want to replace certain characters of our string with a variable, okay? And we can also typecast that symbol using some of these flags, right? And then we can do cool things with it, like we can pad it with a certain width or precision, so if it's point, or we can format it in different ways or add certain flags, like these fields where you're adding like positive values or leading zeros, which is actually what we're wanting to do. Okay, so let me show you an example of how this sprintf would work. Before we go too complicated, let's just say I want to say hello underscore, and then I'm going to put a this percentage sign and s, okay, which is going to show that the variable that I'm wanting to reference is a string, okay, and I close the quotes, right, and then I'm going to feed it a variable here. So I want to type world, okay, and end that. And what it's going to do here is create a string. It's going to return a string that says hello world, right? Now I've given it just a basic string here. I mean, I could have typed the words hello world. But the thing is, this could be a variable. This could be an attribute that is already created on our points. So we maybe already have something here that has created that s@foo equals world. Okay. And now we want to reference a variable inside of a string. So we want to say s@foo. Okay. Now you'll see it still gives the same result, hello world, because it's referencing a variable. But we can't do that inside of a string. We can't just go say s@myid2 equals, and then just give it a string and say hello, and then give it s@foo, because you see it once what that's going to return is that, okay. This is not what we want. This is basically telling us that it's referencing a bound foo variable, okay. That's not the result we want. We want it to actually evaluate the bound foo attribute, okay. So the sprint function does that for us. And now moving back to our example, what we're going to do is feed it our IDs instead of this foo function. So we're going to say percentage, and then our ID is an integer, so we're going to say I, okay, and then we're going to feed it the ID, so I@ID. Okay. So now what you'll see here is we have an ID, and well, my ID, and we also have ID, and they look identical, but they are actually not, because the one is you'll see here, ID is an integer, but my ID is a string. Okay, and that means that we're going to be able to concatenate things correctly. Okay, so now the next step of this is also we're wanting to pad this, and this is something that the printf function can do. So we're formatting the string. Now you can reference this if you want to read through it, and it will explain how the leading zeros work, but please be careful. This page it's a very archaic function. This doesn't actually function like a lot of the other vex functions. This one is inherited from C. So it's powerful, but it can be a bit confusing. The syntax of it is a little bit weird, and especially if you're learning all these other vex things, it doesn't seem to function like the other vex functions do. So use the examples. You can kind of read through and see what they're doing, but it doesn't give as much information as I would like, and it is honestly quite confusing. So I'm going to talk you through it rather than, I mean, you can try read this all, and hopefully it'll make a little bit of sense, but yeah, I don't know, sometimes I still forget how to use this function because it's just the help file is so bizarre. Anyway, what we've got is the percentage sign here and the I. Now, when we want to put a numeric like leading zeros, we actually put the value between the percentage and the casting. So we put a 0 to show that we want to pad it with zeros. And then we give it a number to tell it how much we want to pad it. So we say 0, 3, and then an I. So percentage, which says replace this character with variable number 1 in our list, because we can have a list of variables, which I'll show you now. So it's going to replace this with the first argument that it finds, but it's going to pad it with zeros. How many zeros? Up to 3 digits, and then it's typecasting it to an integer. Okay, so if I click away or hit insert, you're going to see the result. So it's padding 0 becomes 0, 0, 0, 1 becomes 0, 0, 1, and you'll see it's padding to 3 digits. So it's not adding 3 zeros at the front, it's making sure that there are 3 digits. Okay, right. Now we're going to do the exact same thing to reference another variable. Okay, if we put another percentage sign inside of here, okay, so within the same string there are 2 percentage signs, what it's going to do is look for a second argument here. Okay, and we want our IDs to be padded 0, 3, and it's going to be another integer. Okay, now for now I'm just going to put back in the same ID just to kind of show you that it is working. So you'll see it's because they're one after another in the string, it's literally putting the ID and then the ID again. Or we could over here, we could put an underscore or something like that, and you'd see it would separate it with an underscore. Okay, which you're welcome to do if you prefer that. But I just like this kind of serial number look. Okay, but this second one, in fact, to be honest, this first one is what we're actually wanting to replace. Instead of using ID, we're wanting to access our primitive number from this, or essentially our copy number. So this number over here. Okay. The reason I want to replace this first one is because I just like the kind of putting the primitive number first and then the point number second. It just makes more sense to me, but it would still give you a unique ID whichever way around you did it, but it just visually it seems right to put the primitive number first and then point number or point ID second. All right, so I'm going to replace this one, and we're just going to do something similar to where we did the attribute promote, where I'm just going to be referencing a primitive. Okay, so I'm using prim to reference a primitive attribute. So here it is, right? So we're giving it geometry. So which geometry are we referencing? We're referencing ourself, so 0. What is the attribute name? Is copynum. And then what is the primitive number? And it's very similar to when we did the attribute promote. You can basically, the points, even though we're running over points, the points know which primitive they're attached to. So if you use @primnum, it's going to return that primitive number. Okay. And this is not working. Let's try and figure out why. Oh yes, right. So this is actually good. This is going to happen to you often if you don't typecast things correctly. Now, in this case, the typecasting is not actually that obvious, right? But if you, I'm going to have another lesson in the future when we get to much more advanced fix, where I talk about how to debug actual errors. When you get certain errors, how to read those and know what it means, so how you know how to fix it. Okay, but this is just a one that you'll come across often. So it says an ambiguous call to a function, right? So it's looking for either an integer, string, integer, but that's going to be returning a matrix 2 or a matrix 3 or something like that, okay? And so on, all of the different types. So essentially what it's saying to us is, I don't know which one. If you look at our function over here, it says type. It doesn't say integer, it doesn't say string, it says type. So it can return any type. It depends on the type of the attribute, right? But it's going to have to access that attribute, an integer or a string or whatever, in a different way. So it's relying on us feeding it a type in order to know how to run this function. Okay? And if we just ran a primitive function, if we were just storing it in a string function, so we just say s at foo equals, and then we ran the prim function, because we're storing it in a string, it knows, okay, I need to run the string version of this function because I'm clearly looking for a string. Okay, the result of this function needs to be a string because it's being stored as a string. In this case, though, it doesn't know, because the result of this, like this s where I'm storing it, I'm storing this value in a string, is coming from the sprintf. The printf function is wanting to place this result inside of here, but this could be anything. And sure, yes, we're casting it here with an I. But this is one of the drawbacks now of this kind of older or more archaic function, is that the casting is happening in here. This prim function has no idea that we're meaning for it to be an integer. Okay? So all we need to do is cast this. And this is one way that you can cast things when it is ambiguous, is you simply wrap it with the class. Right? So we're going to say int, and then we wrap it in a function. Okay? And now you'll see it works. Okay. So I actually forgot that was going to happen on here, but I'm glad that it did, because it's actually a good moment to show you that sometimes if you get that ambiguous call, it just means, so if you see it says the word ambiguous call to function, it just means that it doesn't know which type, and you need to just be more explicit with which type you're meaning to run. Okay, so now you'll see we have 000, we've got 00001, and so on. All these IDs should be 100% unique. There should be no duplicates, and yet from this information, from this one ID, we can actually extrapolate what the ID number was, so the point ID, and what the primitive ID was. So these are all part of primitive 0. And actually, to prove that, I'm going to quickly just attribute promote the from primitive to point. I'm going to just copy the copy number down, just so you can see it in here. Okay, so there we've got our copy number, which is 0. Let me just get rid of this world thing. Okay, so we got our copy number, which is 0, we got our ID, which is 0, and now our custom ID, our unique ID that we've created, is 0000000. Same as here, with 0 and 1 become 0000001, and so on. Okay, if we go further down, better examples, 4 and 76, there's 4 and 76, but in a unique serialized ID like this. Okay. So then from this, we'll be able to use our color over here and reference my ID as the driver attribute for our random, and we'll get a totally unique, so you'll see even at 0, so our first points on each primitive still have a unique color, because they're referencing a unique ID, as opposed to if it just referenced ID, then the first point on each of these particle systems would have the same shared color. So it depends what result you want, whether you want this symmetry of randomness or whether you actually want true randomness. You can then use your unique ID. Okay, so I know this one has gone on a little bit long, but this is quite complex. So, but you will actually use this surprisingly often. So if you're ever struggling to create unique IDs after some sort of geometry generation, whether it's a copy or a simulation, something like that, then just remember this trick, this technique. Okay, so thanks guys, and we'll do one more example and then we'll wrap it up. Okay everyone, so the final example we're going to do here is UV sampling using Vex. So I've got the toy, the rubber toy, just because it has UVs already. And what we're going to do is reference these UVs and grab some sort of attribute. Okay. In this case, we're going to just be grabbing point position from a particular attribute, a UV coordinate that we feed it, but you can grab anything you want. So it's a really cool way of just kind of sampling things from, instead of at each point, which is quite limiting, you know, you have to sample at this exact point or that exact point, but instead, if you can sample at a UV coordinate, then it means you can grab point position somewhere in the middle of this primitive, you know, or you could grab color at exactly this point, or figure out what its, you know, shader values are, or you know, there's a lot of cool things you can do using UV sampling. Okay, so the expression we're going to be using is just quite as simple as UV sample. So I'm going to hit F1 on this and show you what this function is going to, how we're going to build this function up. Okay, so it interpolates the value of an attribute at a certain UV coordinate, right, using UV attribute. Okay, so we do need UV attributes to already be on the geometry, which we do have now on this toy. And then we're going to be feeding it a certain UV coordinate that we want to read from. Okay, and it can return any type, including arrays. Right. So in this case, we're going to be just saying, I'm going to create a custom attribute called pos for position, because I don't want to change the position of the points on the actual toy. I just want to store this attribute. And then I'm going to, as an example, to just to show you where we're reading, I'm going to just reference this position and copy a sphere onto that point. Okay, so because we want to do just one particular point, so we want to do this once, I'm going to change the run over to detail, which runs only once. Okay, because we're wanting to just sample one particular UV coordinate, not one per point. Okay, which would be then 12,874 times. We don't want to do that. Okay, so if we switch to detailed, this whole script is going to run one single time for the entire piece of geometry. Okay, so we say v at pos equals, and then we run our UV sample. Now UV sample wants the first argument to be the geometry, so that's 0 because we're reading from our first input, and then the attribute name that we're wanting to reference. Now I just want to reference point position at that particular UV coordinate. Okay, so I'm going to put capital P for point position, and then I need to feed it a string of the UV attribute, because your UVs can be named something else. They are not necessarily named UV. In this case they are, but if you happen to have them named whatever, then you just type whatever. Okay, and then here this vector UVW is the coordinate that we're looking for. Okay, so we're going to give this a reference, so we're going to say channel V, so we're going to create a channel reference on this wrangle. We'll create a vector channel, and then we can just kind of alter those values and read from a particular UV coordinate, and we're going to just call this UV or something like that. Right, and it's that simple. So we click the add spare parameters, and we get this vector parameter, and we can choose which part of the UVs to sample from. Okay, and what this means here, what this relates to, is our actual UVs. So if I go set view to the UV view, you'll see here this is all unwrapped on our UV set, and this is 0, 0 at the bottom. So this is then 0, 1, this is 1, 0, and this is 1, 1. So 0.5, 0.5 would be exactly here in the middle. Okay, so let's do that. You see here we actually have an island in the middle here at 0.5 and 0.5. So if I set this to read on 0.5 on X and 0.5 on Y, which the X and Y relates to our U and V, then we should end up with the reading or sampling the point position value at this coordinate. Okay, so right here at 0.5, 0.5, not at the points themselves, but at the UV coordinate at this location. Okay, which is what's really powerful about referencing UVs, is now we can get stuff in between primitives instead of only having to read from the points themselves. Okay, so what I've got prepped just to show you how it works, so I've got this little network here. I just have an add node which is referencing that detail attribute. Okay, so detail, then I'm pointing to attribute wrangle 1, grabbing the pos, grabbing the first component, which is X. This one is doing the exact same thing, but grabbing the second component, which is Y, and then this is the third component, which is Z. Onto that, I'm then creating a small red sphere, copying it onto that point, and then I'm just going to merge these two so that's easy for us to see them. Right. And you'll see right there that, in fact, let me make the sphere a little smaller so that we can see where it lives within the point. So it's not actually on the point, it's somewhere in the middle of that primitive. And if I go back to our UVs, you'll see that that's exactly where this is located, at 0.5, 0.5. Okay, so you can reference anything, point position, but you could do, I don't know, anything. And you'll see as I slide this value, it's sliding along the geometry, but it's not sliding along the primitives or the points, it's sliding along the UVs. Okay. All right, so that wraps that up. All right, everyone. So I hope that all makes sense. I hope that you were able to follow along with these practical examples. I'm sure you'll find them quite useful, and we'll use them often. But remember, this is the foundation of everything else that we're going to be building on. So if you can do these, then you can do more advanced expressions. Everything, it all boils down to the same thing. It's just that our more advanced scripts are just going to have, more expressions and maybe a few more conditions and blocks and things, but it really boils down to the same thing. If you're unable to follow up to this point and you're confused, please make sure that you get to a solid point. Make sure you can follow these, go back a little bit, do a little bit of extra research, ask some questions, because it is going to get pretty advanced after this, and if you fall behind now, it's just going to become confusing and frustrating for you. Okay, but if you are keeping up, then great, and I'll see you guys in the next week, in the next lesson, where we're going to be talking about the more advanced side of Vex, all the kind of advanced expressions, different things like blocks and how to work with arrays and strings, and it's really, really fun stuff, and it opens it up to you. When you know all of this, you'll be able to essentially do anything with Houdini. Okay, it's like you're communicating directly with it, and you can tell it whatever you want and you can get the result that you need. Great. So I'm very excited to move on to that, and I will see you guys in the next lesson.